Okay, so the second speaker today is Shaoyun Bai from Princeton University. He will talk about SUN Casson invariants and symplectic geometry.
Yeah, okay, so thank you, Zhengyi, for the introduction. So it's a great pleasure to speak in the question of the Zoominar. So today I'm going to talk about SUN Casson invariants and the symplectic geometry. So by the way, I'm a student of John Pardon, who's obviously not in the audience. Anyway, so let's start. So this talk has three parts. The first part is about some introduction to the background of this problem I will talk about. And second part, I will give a sketch of the technical construction, but I won't maybe not go too deeply into that. And in the third part, I will just give several further questions related to the results I will present today. Okay, so let's start the first part. So let me introduce this Casson invariant very briefly. So in the year 1985, Casson introduced an invariant for oriented integer homology 3 spheres. So for those of you who is not so familiar with two-dimensional topology, integer homology sphere Y will actually be a closed smooth 3 manifold such that its homology with integer coefficients is isomorphic to the integer homology of the 3 sphere. And roughly speaking, the Casson invariant is defined by counting irreducible SU2 representations of the fundamental group up to conjugation. So to explain it further, we say a representation, SU2 representation, is called irreducible if the commutator of its image is equal to the center of the SU2, namely just a +1 or -1. Otherwise, we call this representation reducible. So this invariant introduced by Casson has many topological applications. For example, it is used to show the existence of a non-triangulable form manifold. Also, it has some kind of surgery formula. And for those of you who are more familiar with fluid theory, the Casson invariant is actually the Euler characteristic of the SU2 incident fluid homology for integer homology 3 spheres. Okay, so now let's give a construction of the SU2 Casson invariant. So it's defined by some kind of intersection number of submanifolds coming out from a splitting of a 3 manifold. So let's say Y is our integer homology 3 sphere, and we take a Hegel splitting of this 3 manifold. It means that the sigma here is a Riemann surface, which is embedded inside our integer homology 3 sphere, and H1 and H2 are 3-dimensional handle bodies with boundary given by sigma. Then we look at SU2 character variety of the manifolds appearing in its decomposition, namely the space of SU2 representations up to conjugations. And then the representation variety of the fundamental group of these two handle bodies could be viewed as subsets of the character variety of the fundamental group of our Riemann surface sigma. And by the Seifert-van Cappen theorem, the character variety of our 3 manifold Y is actually equal to the intersection of the character varieties of the fundamental group of our handle bodies inside the character variety of the Riemann surface. So this is the schematic picture of the situation I just described. So here on the blue line and the right line are the representation variety coming out from the handle bodies. And note that there's a distinguished point here. It's called a reducible connection or reducible representation of the fundamental group. So in the case of integer homology 3 sphere, the reducible representation of fundamental group is actually unique up to gauge transformation, which is given by the trivial representation of the fundamental group of our 3 manifold Y. So now we have a manifold, background manifold given by the character variety of our Riemann surface, and we have two submanifolds inside. And the Casson invariant is actually defined to be the, roughly speaking, the intersection number of these two character varieties inside this bigger character variety. And it actually turns out that the intersection number is always even. And the Casson invariant in reality is defined to be 1/2 times the intersection number I described before. So that's the very quick sketch of the construction of SU2 Casson invariant. Then I'll talk about the extension of Casson invariant to SUN. So it's a very natural question to ask how to extend the definition of Casson invariant to SUN or more general compact Lie groups. So this question actually has a relatively long history. So for example, there's a survey paper written by Attia back in 1988. The title is New Invariants of 3- and 4-dimensional manifolds. So in this paper, Attia commented, in principle, the SU2 here could be replaced by SUN, but then more care would be need to be taken with the reducible representations. Recall that in case of SU2, we actually have just one reducible representation up to conjugation. And the Casson invariant of SU2 is just defined by throwing away this unique reducible representation. So to illustrate the difficulties caused by reducible representations, note that the fact is reducible representations are no longer isolated for the case when n is greater than or equal to 3. So as a result, the character varieties I introduced before will have singular points. So it's hard to make perturbations and to define the intersection number using differential topology. And even if transversality could be achieved, the naive definition of intersection number might actually depend on the perturbation. So one might need to introduce some new ideas to actually define an intersection number, which is not depending on the perturbation. And yeah, this question has been asked maybe after the introduction of Casson invariant back in 1985. So then there are a lot of follow-up works trying to solve this problem. So notably, there is a work of Boyer and Nakas. They actually define a version of Casson invariant for all compact Lie groups. They just care about irreducible representations and throw away all reducible representations. In particular, their invariant is not perturbative, so they don't have a surgery formula or topological application. And Walker, in the year 1990, introduced SU2 Casson invariant for integer homologous, for rational homologous spheres instead of integer homologous spheres. So in that case, Walker needs to deal with reducible representations, and his work actually serves as one of the motivations for the constructions I will present today. Then also in the year 1990, there's an announcement published in Bulletin of MS by these three people, Campbell, Lee, and Miller. So they try to define Casson invariants for the singular character varieties and consider their intersection number. They claim to use some transversality result established by Berestone back in the 70s. But unfortunately, their construction never came out because of technical difficulties. And then there's also a work by Curtis on trying to define Casson invariant for Lie groups given by SO3, U2, spin4, or SU4. But fortunately, for these constructions, essentially all the Casson invariants with coefficients inside these Lie groups are actually reduced to SU2 Casson invariants. So parallel to the construction using intersection theory, there are actually constructions coming out from 3-dimensional gauge theory. So the most notable work in this direction is the construction of tops back in 1990, and he worked out the case for SU2. Then after 8 years, there's a work of Bode and Herod generalizing tops construction into SU3. Moreover, in Tops' paper, he proved something more. He shows that the gauge theoretical definition actually equals Casson's original intersection theoretic definition. So that's roughly speaking on the history of this problem. And if one tries to relax on or generalize on the conditions satisfied by this Lie group, there are of course other constructions like recent work of Abzai and Manolescu about defining actually fluid theory with Lie group given by SL2C. But that's not the focus for today. Okay, so now I'm ready to state the main result. So there's a paper I wrote with Boyu Zhang, who is also from Princeton last year. So we actually generalized the definition of the Casson invariant to SUN using gauge theory. And then there are more recent work of myself saying that the SUN Casson invariant is actually equal to a version of equivariant intersection number of character varieties. So to understand this theorem, it says that the above theorem actually extends Top's result to all SUN. And this could be thought as a version of the equivariant decategorified Atiyah-Floer conjecture. Okay, so this is the first part of this talk, so I think it's a good time to pause for questions. So is there any question about the main result I just stated?
Just to clarify, you said the character varieties have singularities. Which one has singularity? The one of the surface or the one of the handle bodies?
They all have singularities.
Okay, I see.
Mm. So any other questions? Okay, great. So now let me try to tell you a little bit about the constructions. So that's the second part of this talk. So let's try to set up the problem. So recall that our integer homology sphere Y has a Hagar splitting. The sigma is a Riemann surface, and H1 and H2 are three manifolds with boundary given by sigma. And to introduce some other notations, let G be the Lie group SUN, and let small g be its Lie algebra, small SUN. So instead of dealing with orbifolds with singularities, there is a very nice work of Lisa Jeffrey back in the 90s, where she constructed something called the extended moduli space. I will not give you the definition of this, but the thing to keep in mind is this is a Hamiltonian G symplectic manifold. So in particular, it has a moment map. The nice property of this extended moduli space is that the moment map reduction of this extended moduli space is actually naturally isomorphic to the G character variety of our sigma. Moreover, these two handle bodies actually define G equivariant Lagrangians Li inside this extended moduli space. And there are also the facts saying that the G orbits of this Lagrangian intersection would actually have one-to-one correspondence with congruency classes of representations from pi1 of Y to G. So the good thing is there is an open part of this extended moduli space which is smooth, and our equivariant Lagrangians L1 and L2 all stay inside the smooth part of this extended moduli space. So instead of dealing with orbifolds and singularities, we'll actually study the equivariant geometry inside of orbifolds. Okay, so then after introducing the equivariant Lagrangians, let me talk about the transversality result I need to give the construction. So now let's introduce the definition. So remember here, L1, L2 are actually G equivariant Lagrangians. So we say that they intersect non-degeneratively if L1 and L2 have clean intersection along each orbit, which is contained in their intersection. So remember that L1 and L2 are actually G equivariant in particular. So as a result, if they have an intersection, the whole orbit passing through their intersection point actually is contained inside their intersection. So that's the definition of non-degenerate intersection. So the transversality proposition entering the construction is, so L1 and L2 will intersect non-degenerately after a generic G equivariant Hamiltonian perturbation of L1. So the proof of this proposition actually is inspired by Wendell's recent work on the superrigidity conjecture. And actually, there is a parametric version of this proposition saying that one can also analyze the wall crossings of intersection when deforming the Hamiltonian perturbation in a generic one-parameter family. And there is a certain classification result about the wall crossing behavior, but I won't state it here. And go back to our geometric situation. For this symplectic manifold extended moduli space, the Hamiltonian perturbations could be related to the so-called holonomic perturbation on the three-manifold Y, which enters the construction of Casson invariant using gauge theory. Holonomic perturbations over there are used to achieve transversalities. And there's a fact saying that we actually have a correspondence. Perturbed intersections between our Lagrangians coming from handle bodies will actually have one-to-one correspondence with orbits of perturbed flat connections on the three-manifold Y. So that's the transversality part of this construction. So is there any question about this? Okay, seems no, that's great. Then, so now let's pretend that we have established the transversality we need to define the intersection number. And now we need to introduce some other definition to actually make the definition work, make the definition of intersection number work. So for this moment, let's just assume that these two Lagrangians would actually intersect non-degenerately inside our extended moduli space. And for each G orbit of the intersection, after certain choices, one can actually define a version of equivariant Maslov index. And note that previously I stated that there's a correspondence between intersection orbits of these two Lagrangians with perturbed flat connections on our three-manifold Y. And using this correspondence, and if we think this orbit as a flat connection on Y, there's actually a notion of equivariant spectral flow. So there are theorems saying that we actually have an inequality, we have an equality relating the Maslov index and the spectral flow. So the proof of this theorem actually combines manifold splitting techniques for computing spectral flows, adiabatic limit type arguments, which are used in establishing other Tel-Aviv type results, and also a infinitesimal version of a symplectic slice theorem. So amusingly again, so many ingredients of the proof actually date back to the 1990s, before I was born. And the equivariant intersection number is defined using a weighted sum of the Maslov indices introduced above. And the above identification theorem between spectral flows and Maslov indices identifies the equivariant intersection number with our earlier gauge theoretic definition for the Casson invariant. So to show that this intersection number is a topological invariant of the three-manifold Y, it suffices to show that the gauge theoretic definition is an invariant. So in the third part of this second part, let me talk a little bit about bifurcations. So remember that the intersection number is defined to be the weighted sum of Maslov indices. And so the weight must be chosen so that the weighted sum is actually independent of perturbations. So this actually requires a detailed analysis of the bifurcations when varying the perturbation data. So recall that I said this is reduced to some to the gauge theoretic construction, and this is indeed done in the earlier work with Bo Yu Zhang. So let me just showcase some kind of bifurcation picture that might happen in the case of SU5. So there's a dotted line over here, as you can see. There are two kinds of bifurcations that could happen for this kind of same type of connections or representations. So this kind of dotted line here is actually different from dotted line over here. And also there's a closed formula for the SU3 Casson invariant. Yeah, let me remind you that the SU3 Casson invariant, it was defined by Boden-Herold using gauge theory. And this actually gave a symplectic formula for the Boden-Herold on SU3 Casson invariant. So I will not explain what these notations mean, but let me give a comment that this shows that Borden-Hurl's SU3 Casson invariant is a natural generalization of Walker's invariant for rational homology spheres. For those of you who know about Walker's invariant for rational homology spheres. Okay, I still have 1 minute, so let me just go to the last page of this talk. So there are some further questions based on the results I present today. So it's actually natural to ask for a surgery formula for the SUN Casson invariants. And here's a conjecture. So let's suppose that K is actually a knot inside our integral homology 3 sphere Y, and let Y 1 over K be the 3 manifold obtained from Y by performing a 1 over K dense surgery along K. Then the conjecture says that the SU3 Casson invariant, roughly speaking, grows of the order K to the K squared as K goes to infinity. And if you take the limit of this ratio, that actually recovers the SU3 version of some kind of Casson type invariant. And moreover, an extension of this weighted counting discussed above in the setting of J-homomorphic curves should be related to a symplectic definition of the Kappa-Kummer-Buffer invariants. Okay, so that's the end of my talk, and I'll wait for questions. Thank you.
Thank you. Let's give a speaker a hand. And are there any questions?
I actually missed the definition. You said it's the sum of mu p's?
Not exactly. So there is kind of weighted sum of mu p's. And also mu p, they are defined as equivariant mass of indices. They actually take value inside the representation range of the relevant stabilizers. So there's some kind of algebraic thing you need to do to define this weighted sum.
I see, I see. Can you actually go back to the slides that you were defining and then explaining the proof of invariance? You were using the gauge theoretic invariance, or you were showing gauge theoretic invariance?
Yeah, so to prove invariance, I prove it in a roundabout way. So I first of all show that there is a relation between the gauge theoretic definition and the symplectic definition. And to show that the symplectic definition is a topological invariant, it suffices to show that the gauge theoretic definition is a topological invariant. So that's established in early work with Bo-Yu Zhang.
I see, I see. Is there a purely symplectic way of showing this? You know?
Yes, I'm pretty sure about that, but I mean, historically, we worked out for gauge theory first. So, I mean, the focus of the second work is really about a TF-Flirt type result, and I don't want to the papers to be too long. Yeah.
So what about the categorized TF-Flirt?
Yes. So yeah, there are many groups of people working on the SU2 case, or they actually don't care about reducible connections. And for higher rank D groups, if one want to take care of the reducible connection, reducible representations, there is no definition of the relevant Flirt theory. And moreover, the Euler characteristic defined over here, according to some experts I talked to, is related to the so-called Braden homology. But for Braden homology, there's, as far as I know, no more theoretic construction in the finite dimensional case. So yeah, it's hard to say any if there exists any categorification at this moment, because I haven't understood the case in finite dimensions. But once it's defined, I believe that there should be a categorified version of the TF-Flirt conjecture in the invariant case.
Okay. Are there any other questions?
Oh, there's.
Could you please expand on this last comment which you made? on a connection with the other conjecture, the last statements which you've made, please.
So sorry, I don't quite understand the question. So expand which one?
You've mentioned the connection with the conjecture of Gopakumar and
Oh,
Vatva.
Yes. So let me go to that slide. I think my screen got stuck. Let me. Yeah, okay. No. Yeah, this one. Right. So yeah, as I said before, the causality proof is actually based on Windows' recent proof of superpositive conjecture. So roughly speaking, yeah, let me just give a very quick introduction for the superpositive conjecture. So it says that for a symplectic RBL 6 manifold, let's say we have a J-homomorphic curve. Then there is kind of multi-covered simple dichotomy telling you that this J-homomorphic map could be factored as a composition of a branch cover to from this domain of this Riemann surface to another Riemann surface, and a simple J-homomorphic map from this second Riemann surface to a symplectic manifold. And using this decomposition, one can define the so-called normal Cauchy-Riemann operator for this multi-covered homomorphic curve. And the superpositive conjecture, roughly speaking, says that, well, if you consider the normal Cauchy-Riemann operator of an arbitrary J-homomorphic curve, and if you have a generic choice of your almost complex structure, the kernel of this normal Cauchy-Riemann operator is actually trivial. So it means that this curve could not be deformed in some sense. So with this result, one can try to ask oneself that is it possible to define an invariant of a symplectic 6 manifold by counting embedded J-homomorphic curves together with some kind of I mean, it's not a naive count. That will be a weighted count, which depends on maybe the J-homomorphic curve you have taken. So this is related to what I present today. It is because, well, both stories care about equivariant transversality, and both stories are about counting objects which are simple in some sense, but you need to take some kind of weighted over these simple objects and try to show that this is an invariant. So that's the similarity at the technical level. And let me also try to make a comment that so there's this top square-morphic invariant defined in dimension 4, so which is kind of different from the usual construction of Gromov-Witten invariants. So TOPS also studied say some kind of weighted count of simple curves in dimension 4, and he indeed defined an invariant, which is not exactly the same as Gromov-Witten invariants, but there is a relation between them. So in dimension 6, there is magical formula conjectured and proved by Neil Parker by Gopakumar saying that the Gromov-Witten generating function could be governed by a sequence of integers. And Neil Parker's proof is not constructive. So it's reasonable to ask if there are any geometric construction to realize its integers appearing in the formula. And it might be related to a generalization of TOPS construction in dimension 4. And now we have Windows transversality result, which is parallel to TOPS result in dimension 4. TOPS also prove a transversality result. So it's interesting to speculate that an extension of TOPS method will actually give a definition of these integers entering the Gopakumar formula. Thank you.
Thank you very much. Thank you.
I think there's a question from the chat, so I cannot see the chat. So can anyone tell me what the question is?
Be a direct message to you. We don't see it.
Yeah, we could talk about infinite dimensional Britain homology and more theorem. We couldn't. Okay, that's a common. Okay, okay. Thank you.